On the 16th of July, 1945, a small group of scientists stood at a distance from a strange tower and a device they'd built in secret. The test had a name, Trinity, and it was scheduled for 5:29 a.m., Mountain War Time. In a few minutes, they would create a light brighter than the sun. Not from a star, but from an idea, a human idea. What most people never hear in the famous retellings is the quiet edge of dread that lived behind the calculations. Months earlier, there had been serious discussion, real math, real debate about whether the explosion could trigger a chain reaction in the air itself. The probability was vanishingly small, but in some minds it wasn't entirely zero. The atmosphere might burn, the world might end, and yet the button was still there, waiting. So, imagine the moment. Oppenheimer and the others, brilliant, exhausted, trembling in ways they wouldn't admit, hovering near that final switch, one finger away from proving a theory, and gambling with the only home they had. Not because they wanted destruction, but because curiosity and necessity can blur into something that feels like fate. Then it happens. The button is pressed. The sky erupts. For a second, the universe looks rewritten in white fire. And the air does not ignite. The atmosphere holds. The world remains. But everything changes anyway. Humanity steps into the nuclear age, and a new question is born. Are we unconsciously risking self-destruction through the very act of understanding? Now here's the unsettling turn. Modern physics whispers that Trinity may have been a metaphor. Because the deeper we go into reality, the more we discover that even empty space isn't empty. And some of our best theories suggest the entire universe might not be perfectly stable at all, just temporarily holding together. So what if space-time itself is sitting in a delicate temporary state and, in principle, could collapse into something else? Stay with me, because by the end of this video, nothing will never mean what you thought it meant. For most of the day, the universe feels like the background hum of a refrigerator. Steady, unquestioned. A kind of cosmic wallpaper that has always been there and always will be. Until something in the middle of the night makes you wonder whether the hum is actually a kind of question. In physics, the word that hides behind that feeling is stable. It sounds reassuring. It sounds like a promise. To a physicist, a stable universe is not a mood, but a position in an energy landscape. Imagine you have a small ball and a smooth bowl. You drop the ball into the bowl, and it rolls around for a while, losing energy, until it settles right at the bottom. If you tap the ball might jiggle. If you nudge the ball, it might climb a little way up the side and roll back down. No matter what small thing you do, it comes back to that same point. That is what stability means here. The universe, as a whole, sitting in the deepest possible valley of energy. Disturb it a little, and it eventually returns to where it was. This is one of the quiet assumptions baked into our everyday lives. The idea that, underneath all the noise of weather and politics and personal crises, the underlying rules are constant. The speed of light, the mass of the electron, the strength of the forces that hold atoms together. They are the invisible floorboards under everything else. But there is another kind of almost stable that hides in the same language. Metastable. It sounds like a small adjustment, a technical detail. In reality, it is a different picture. Now move the ball from the bowl to a hillside. The hillside is not perfectly smooth. It has dents, little pockets where the ball can get trapped. You place the ball in one of those dips. It settles. If you look from very far away, you might not even see the slope. The ball looks still, comfortable, safe. If you nudge it gently, it rolls around inside the dip and comes back. For all practical purposes, for a very long time, it behaves as if it were in a true valley. But it is not. If the ball somehow gets just enough energy, or if the dent is shallow enough for quantum randomness to help it, there is a chance it will escape. It will slip over the lip of the dip and start rolling down the larger hillside, toward a deeper valley that you could not see from your first perspective. Once it escapes, there is no going back. The previous stable position is revealed as temporary, a pause, not a destination. That is metastability. Not a dramatic cliff, but a very long-lasting illusion of permanence. When physicists use this word about the universe itself, they are not trying to be poetic. They are looking at numbers that came out of particle colliders, feeding them into theories, and asking a blunt question. Is our cosmic ball in the deepest valley, or in a long-lived dent on a slope we barely understand? This question became sharper when a particular field entered the story. The Higgs field. Unlike many fields in physics that switch on and off in different places, the Higgs field is thought to fill all of space, all the time. You are not separate from it. Every particle with mass is interacting with this invisible medium. The way a swimmer is always in contact with water, whether they notice it or not. The shape of the Higgs field's energy as a function of its value is called its potential. On a graph, it looks like a landscape. For a long time, that landscape was theoretical. Physicists could draw possible shapes, but they did not know which one nature had chosen. Then, at a giant ring of magnets buried near the border of France and Switzerland, protons were smashed together at extreme energies. On a summer day in early July of the year 2012, two big experiments announced that they had found a new particle with a mass of about 125 giga-electron volts. That particle behaved in a way consistent with the long-predicted Higgs boson. The missing piece of the standard model seemed to slide into place. Outside physics, headlines reached for drama. The God particle. The end of a long hunt. Inside the community, the mood was more complicated. Excitement, yes. Relief, yes. But also a strange deepening of a quieter worry. Because once you know the mass of the Higgs boson, and you combine it with other key numbers like the mass of the top quark, you can plug those values into equations that describe how the Higgs potential behaves at very high energies. You can ask, if we trace this energy landscape far beyond what we can reach in the lab, does the valley we live in continue downward to a true bottom, or does the slope eventually bend in a way that reveals a deeper valley somewhere else? The calculations, done and redone by different groups, seem to place our universe unsettlingly close to the boundary between two regimes. Truly stable and metastable. Not obviously doomed, not comfortably safe, balanced near a line on a diagram, like a city built near a fault zone it only recently discovered. Picture that hillside again. The ball in the local dent, not teetering at the edge, not about to slide, but not truly at the lowest possible point either. Given enough time, or an extraordinarily rare quantum event, there is a non-zero chance it could tunnel through the small ridge that holds it and appear in the deeper valley beyond. The transition would be sudden and irreversible. The landscape would not be what we thought it was. Some physicists and science writers started using darkly playful phrases. The Higgs abyss. The big slurp. As if the universe might, in principle, be swallowed by a deeper form of nothing. Not because of anything we do, not because of a button we press, but because of the structure of the energy fields that underlie reality. It is important to be precise here. These calculations do not say that such a transition will happen soon. The timescales involved, if the vacuum is indeed metastable, are so astronomically long that they make the age of the current universe look like the lifespan of a soap bubble, and small uncertainties in the measured masses can push the conclusion around. Slightly different values could move us into the safe, truly stable region, or into a more dangerously unstable one. But the psychological effect of the idea does not care about those reassuring qualifiers. That small word, metastable, opens a crack, because we are used to thinking of the laws of physics as the final frame. Weather can change. Species evolve. Civilizations rise and fall. Stars live and die. All of that happens within a fixed rulebook. Gravity does what gravity does. Quantum mechanics does what quantum mechanics does. The identities of particles, their masses and charges, the strengths of their interactions, Those are the constants, the way the game board is carved. Vacuum metastability suggests something more delicate, that the rulebook itself might be a product of a particular state of the vacuum, that what we call empty space is not a neutral backdrop, but a specific configuration of fields, sitting in a valley in an energy landscape that might have other valleys, and that, at least in principle, the universe could undergo a phase transition in which that configuration changes. And with it, the rules. The closest analogies we have are mundane: water freezing into ice or boiling into steam. The same H2O molecules, different arrangements, different phases. In one phase, you can swim. In another, you can skate. In another, you can inhale the same substance as vapor. The differences are not just cosmetic. They change what kinds of structures can exist. Our universe, according to modern cosmology, has already gone through such phase transitions. In its earliest fractions of a second, as it expanded and cooled, fields shifted, symmetries broke, forces separated from a unified state into the distinct interactions we see today. The Higgs field itself is thought to have changed from a state with zero value to one with a non-zero value everywhere, reshaping the masses of particles and making atoms possible. So the idea that we might not be in the final phase is not a wild departure. It is an extrapolation, a suggestion that there might be more chapters in the book of physics than the ones we have read so far. The emotional tension lies here. We evolved in a tiny, stable-seeming corner of this unfolding. Our nervous systems learned to treat the local environment as basically reliable. The ground is solid. The sunrise is regular. The constants are constant. That sense of "this is how things are" is baked into our language, our institutions, our expectations of tomorrow. To find out that, deep below those expectations, there is an energy landscape in which our entire vacuum could be a long-lived but temporary configuration, is like discovering that the continent you live on is actually a vast, slow-moving raft of rock floating on molten stone. Day to day, nothing changes. But once you know, you cannot entirely unknow it. Some physicists respond to this realization with an almost aesthetic appreciation. The parameters of our world happen to place us near a strange boundary where stability and metastability meet. It could be an accident. It could be a clue. Perhaps new physics beyond our current theories will one day explain why the numbers fall where they do and whether the apparent near criticality is meaningful or not. For the rest of us, the meaning is less about future calculations and more about a subtle shift in perspective. The universe that felt like a fortress begins to resemble an elegant suspension bridge. Every cable tuned, every piece balanced, strong enough to carry enormous weight, yet clearly the product of specific conditions, not an eternal, indestructible monolith. Nothing in your living room changes when you hear this. The chair under you does not flicker. The walls do not hum. But something in the background, sense of security, reorients, even if only slightly. The question is no longer, is the universe safe for us? But, are we perhaps reading too much permanence into a reality that might only be holding? For now, and underneath that, a quieter realization waits. To understand why metastability matters, and how we even reach the point of asking whether the vacuum itself is temporary, we have to go back before colliders and quantum fields. Back to a time when nothing was not yet an energy state, but a philosophical fear that haunted a person staring at the world and wondering what, if anything, could be trusted. It started as a question, not about energy landscapes or quantum fields, but about whether anything at all could be trusted when the world itself might be misleading. In the early 17th century, a man sits at a desk lit by a small window and a candle that is starting to gutter. Outside, Europe is tangled in wars of religion, shifting alliances, and a slowly emerging scientific culture. Inside, René Descartes is wondering how far doubt can go before it erases the very ground he stands on. He is not thinking about Higgs fields or cosmic vacua. He is thinking about the possibility that his senses could deceive him, that dreams can mimic waking, that even logic might be manipulated by some malicious intelligence. So he strips everything away. He imagines that every belief that can be doubted has been burned to ash. The external world, other people, even his own body. What remains is not a picture of atoms in a void, but a single fragile certainty, the fact that he is thinking. If he is doubting, there must be a doubter. If he is deceived, there must be something that experiences deception. From that, he writes the sentence that will echo through philosophy. I think, therefore I am. If you seven to rise with peace. For Descartes, this is a kind of emergency anchor. He fears the possibility of nothing, not as an empty room, but as a collapse of meaning. If everything can be illusion, what remains that is unquestionably real? His answer is not a physical vacuum, but a conscious point, a self that cannot be doubted without confirming its own existence. In a way, this is the first move, from a naive trust in the world to a more cautious, layered view. There is the way things appear, there is what can be checked, there is what must be assumed. Descartes does not yet know that. Centuries later, physicists will confront their own version of this problem with experiments that carve holes in the air. Not so long after his reflections are published, another man is facing a different kind of nothing. It is the middle of the 17th century. In a German city, a crowd gathers in a square. In front of them stand two large copper hemispheres that fit together to form a hollow sphere, connected to a crude but ingenious pump. The man in charge is Otto von Guericke, mayor of Magdeburg, and he has arranged this demonstration to make an invisible idea tangible. He pumps air out from between the hemispheres. As the air thins inside, the outside atmosphere presses in. To reveal how strong that pressure is, he has arranged teams of horses, harnessed on either side of the locked spheres. When the signal is given, the horses strain, muscles bunching, hooves sliding on the ground. The crowd watches as living power throws itself against what looks like nothing. The hemispheres do not come apart. In some versions of this demonstration, it is said that as many as 16 horses could not separate them once the air was evacuated. Whether the exact numbers are precise or embellished, the message is clear. What people had casually called empty space turns out to have weight, force, behavior. The air has pressure. Removing it does not create a harmless vacuum so much as it creates a situation in which the rest of the world pushes back. Here, nothing is no longer a purely philosophical horror. It is a physical state that can be produced, manipulated, felt through ropes and animal bodies. Yet even now, the question of whether this is a true absence of everything remains open. Many thinkers still imagine a subtler substance filling space, an ether so fine that even an evacuated sphere could not rid itself of it. A few decades later, Isaac Newton will publish his great work on motion and gravity. In that book, The Principia, he presents a universe of masses and forces, moving through what he calls absolute space and absolute time. Planets orbit the sun, comets swing through the outer reaches, projectiles arc through the air, all according to precise mathematical relations. Space, in this picture, is a kind of rigid, invisible stage on which bodies move. But Newton is not entirely comfortable with one aspect of his own theory. Gravity, in his equations, acts instantly across empty space. The Earth pulls on the moon. The sun pulls on the planets. There is no chain of intermediate gears, no fluid or rope tying them together. When critics ask him how matter can act on matter at a distance with no contact, he does not have a satisfying answer. He famously says, he does not feign hypotheses. In other words, he can write down the law, but he cannot yet explain the mechanism. Once again, nothing turns slippery. It is not just the absence of air. It is a stage that somehow allows force without contact. It looks simple on paper and deeply mysterious in thought. For many people of this era, this picture settles into the mind as common sense. The universe is mostly empty space, with hard particles or continuous matter fields moving through it. The vacuum becomes an abstract background. You can pump the air out of a chamber, and you can imagine removing even more subtle stuff. But you still have the stage itself. 3 dimensions of space, 1 of time, waiting passively. That is the nothing that Descartes' thinking self inhabits, and that Newton's planets traverse. The stage feels stable. Even if bodies move, collide, or explode, the underlying canvas does not tear. It does not flex. It does not participate. Of course, this stability is an assumption. No one has yet run an experiment that directly tests the nature of space itself at very small scales or very high energies. The vacuum, as far as anyone can tell, is simply the absence of matter as they know it. If there are subtler structures, they are hidden behind the limits of technology and the habits of thought inherited from centuries of philosophy and common experience. This is the quiet pattern that will repeat. We treat the unseen as simple until some stubborn phenomenon forces us to complicate it. For Descartes, the stubborn phenomenon was doubt, the realization that senses and ideas can mislead. For von Guericke and his hollow spheres, it was the strength of atmospheric pressure, revealing that empty space between objects could be filled with an active, physical medium. For Newton, it was the success of a law that described gravity precisely while leaving its underlying nature obscure. All of them, in their own ways, are circling the same intuition. There is what we see. There is what we can remove. And beyond that, there is a level of structure we have not yet resolved. In the centuries that follow, attempts to probe the vacuum will grow more elaborate. The idea of an all-pervading ether will rise, offering a substance for light waves to ripple through, much like sound waves in air or ripples in water. Experiments will be devised to detect the Earth's motion through this ether, to see whether the speed of light changes as we move. When those experiments stubbornly report no such change, the ether will begin to die, leaving a deeper emptiness in its wake. And each time a layer is stripped away, the anxiety that haunted Descartes comes back in a new form. If not ether, then what? If not a passive stage, then what holds the rules in place? If the vacuum is not a simple nothing, what kind of something is it? And how stable is that something allowed to be? From a distance, these developments can look like a smooth progression in a textbook. Descartes, then Newton, then the death of ether, then the rise of fields, then quantum mechanics. In lived time, they were messy, contested, full of confusion and resistance. The human mind does not easily give up a satisfying picture of reality, especially one that makes the world feel grounded. What connects them, and what matters for the question of metastability, is the slow erosion of the idea that there is an unquestionable backdrop. What starts as a philosophical worry about illusion and a physical demonstration of evacuated spheres will eventually feed into a more radical shift. The realization that even the vacuum itself is a kind of medium, populated by fields, fluctuations, and energy. A medium that can have different states. A medium that can, in principle, change. But before that realization can crystallize, something else has to happen. The universe has to lose its last obvious invisible substance, the ether, and with it, the illusion that waves always require a material to ride on. Only when that idea breaks does a new one become possible, that fields themselves are fundamental, that space without particles is not empty at all, and that nothing is a restless, structured state that might not be forever. When you start suspecting that the background is not empty, the next unsettling step is realizing that even the invisible things you invented to feel better might have to die. By the 19th century, physics had become comfortable with the idea of waves. You could see them in water, feel them as sound in the air. James Clerk Maxwell's equations, written in the middle of that century, showed that light itself could be understood as a kind of wave in electric and magnetic fields, intertwined and self-propagating. Waves, in our experience, always need something to ripple in. Water, air, a string. So thinkers reached for an old word and gave it a new job. Ether. The luminiferous ether was supposed to be a silent, all-pervading medium filling all of space. It had to be incredibly stiff to support light waves moving unimaginably fast, yet somehow so subtle that planets could move through it without obvious resistance. It was a strange substance, squeezed into contradictory requirements, rigid enough to carry light, gentle enough not to slow the Earth. Still, for many, it was comforting. It restored a sense of materiality to the vacuum. Instead of a barren nothing, you had a ghostly something. The stage had a fabric again. If you had stood in a European observatory in those years and asked an astronomer what existed between the stars, the answer would not have been absolutely nothing. It would have been this invisible sea, the ether. Only cranks suggested otherwise. Then came the quiet work that would unravel it. In the late 1880s, in Cleveland, Ohio, Albert A. Michelson and Edward Morley built an instrument that looked almost disappointingly modest for what it was trying to test. It was an interferometer, a device that splits a beam of light in two, sends the halves along perpendicular paths, and then recombines them. If the speed of light changed slightly along one direction compared to the other, the recombined waves would shift their pattern of bright and dark fringes. That shift could be measured. The idea was simple. If the Earth was moving through the ether, then light traveling along the direction of motion and against it should be affected differently than light traveling sideways. There should be an ether wind, like the rush of air you feel when you stick your hand out of a moving car. By rotating the interferometer and watching how the interference fringes changed, Michelson and Morley hoped to detect this wind. They expected a small but clear effect. Instead, they got essentially nothing. The pattern barely moved. Within the sensitivity of their apparatus, the speed of light seemed to be the same in all directions, regardless of the Earth's motion. This was not an instant revelation. It was a puzzle. Some argued that the ether might contract objects in the direction of motion, conspiring to hide its own presence. Others suggested the Earth might somehow drag a pocket of ether along with it. Theories were patched, modifications proposed. The idea of ether was too entangled with intuition to be dropped overnight. There is something deeply human in that hesitation. When you have built a picture of reality that feels solid, you do not abandon it at the first strange measurement. You bend. You add complications. You defend. Stability, even in theory, is emotionally sticky. But the null result of Michelson-Morley's experiment sat there, stubborn and clean. Other experiments began to echo it. The more precisely people looked for the ether wind, the quieter it seemed to become. Somewhere in Switzerland, a young patent clerk was thinking about clocks, trains, and what it really meant for two events to be simultaneous. Albert Einstein did not begin with Michelson-Morley in his famous paper on special relativity, but the atmosphere of confusion about ether and light formed part of the background. Instead of insisting that light must adapt to pre-existing notions of space and time, he took a more radical step. He proposed that the speed of light in vacuum is the same for all observers in uniform motion, and that the laws of physics must take the same form in all such frames. If those statements are true, then our old ideas of absolute time and absolute space are wrong. Time can dilate, lengths can contract. Events that seem simultaneous in one frame may not be in another. The ether, as a preferred frame of reference, becomes unnecessary. There is no hidden medium defining real rest. There are only relationships between observers, stitched together by a constant speed of light. This was not just a technical shift. It was a rearrangement of what counted as background. Space and time fused into space-time, a four-dimensional arena in which intervals could differ for different observers. Yet the underlying structure of the laws remained consistent. Importantly, though, Einstein did not strip the universe of fields. Maxwell's electromagnetic field survived. In fact, in the new picture, it became more fundamental. You could think of the field as a kind of entity in its own right, not a vibration in some deeper ether, but something that simply exists, filling space, carrying energy and momentum. So the ether died, but something stranger took its place. The vacuum was no longer a substance in the old mechanical sense, yet it was not empty either. It was the place where fields lived. For a while, this seemed like enough. You could imagine In the simplest terms, a universe with particles and fields. Particles moved, fields spread, forces acted. The vacuum was what you got when you removed all the particles and turned the fields down as low as they could go. Nothing, once again, seemed to have a straightforward definition. Then quantum mechanics arrived and quietly smashed that simplicity. At first, quantum theory was about discrete energy levels, quantized orbits, probabilities instead of certainties. It grew out of attempts to explain blackbody radiation, the photoelectric effect, atomic spectra. The focus was on particles and their strange behavior. But as the theory matured, especially in the early and middle decades of the 20th century, a deeper language began to emerge: quantum field theory. In that language, what we call a particle is not a tiny billiard ball flying through empty space. It is a localized excitation of an underlying field. The electron field, the photon field, and eventually many others. At every point in space, each field has a value. The vacuum, in this context, is the lowest energy state of all these fields. But because of quantum uncertainty, lowest energy does not mean perfectly still. Fields fluctuate even in their ground state. The absence of the ether did not leave a clean, quiet emptiness. It left room for something more disturbing: a vacuum that seethes with energy, even when no particles are present. The path from Michelson and Morley's quietly rotating interferometer to quantum vacuum fluctuations is not a straight, inevitable line, but you can trace certain threads. First, the willingness to kill a comforting invisible medium when its consequences do not match experiment. Then, the courage to let go of absolute time and space. Finally, the openness to treat fields themselves as the basic ingredients of reality, even when their behavior resists visualization. Each step erodes some reassuring picture. There is no ether to cradle light. There is no single global time everyone can agree on. There is no perfectly empty void where nothing at all happens. It is worth pausing here, because this cascade has psychological weight. Most of us live with an unspoken model of the world. Objects in a room, resting on a solid floor, surrounded by air, within a stable framework of time. Light fills the space between things. Sound travels through the air. If you strip matter and air away, you imagine a silence, a stillness, a kind of true nothing. The history of physics, from the late 19th century onward, is a long argument with that intuition. When the ether was finally abandoned, it did not mean that reality had become simpler. It meant that some of the complexity was being shifted from a mechanical substance to a more abstract structure. The vacuum, once freed from the need to be a material medium, became available to be reimagined as something like a state of fields. That, in turn, opened the door to asking new questions. What is the energy of that state? Can it change? Does it gravitate? Could it, under different conditions, be different? Notice the pattern. We remove one layer of invisible support, only to discover that the universe still holds. That encourages a kind of intellectual bravado. Perhaps we can keep stripping away and reach something final, something absolutely simple. But what we have actually found, over and over, is not a final bedrock, but a subtler dependency. The stability of what we see depends on structures we did not initially suspect. Those structures turn out to be capable of different arrangements. We are not uncovering an unshakable foundation, we are mapping configurations. This is where the question of metastability will eventually reappear in a more precise form. If the vacuum is a configuration of fields, and if those fields can occupy different states with different energies, then our current vacuum could, in principle, be one phase among others. Not an absolute ground, but a particular choice in a larger space of possibilities. The path to that realization passes through places that do not look dramatic in photographs. Conference halls, chalkboards, quiet islands. In the late 1940s, a group of physicists gathered at a meeting on Shelter Island, off the coast of New York. They were there to confront the growing pains of quantum electrodynamics, the quantum field theory of electrons and photons. Their work would help solidify the idea that quantum fields and their fluctuations are not optional interpretations but necessary parts of the description of reality. From the outside, it would have looked like any other scientific meeting. Talks, discussions, walks along the shore. But in retrospect, you can see it as part of a longer story that began with light waves in an imagined ether and was now grappling with the more unsettling idea that even empty space is alive with invisible activity. Somewhere within that shift, the old comfort of a simple, passive vacuum evaporated. In its place, a new picture began to sharpen. The vacuum, as an active participant in physics, with energy, with structure, with a history. Once you accept that, another question becomes almost impossible to avoid. If the vacuum is something that can be shaped, can fluctuate, can influence the motion of matter and the expansion of the universe, then what guarantees that the particular state we inhabit is forever? Maybe the strangest part is that forever turned out not to be the first thing we had to give up. Before we could even ask whether the vacuum might change, we had to accept that nothing refuses to sit still. The shift became concrete in a small, almost secluded setting. In the late 1940s, on an island called Shelter Island off the coast of New York, a group of physicists gathered in what looked, from the outside, like a quiet retreat. Inside the meeting rooms, they were wrestling with something that sounded more like a bookkeeping problem than an existential crisis. Infinities in their equations. They were trying to understand the quantum theory of light and matter, quantum electrodynamics, the theory that describes how electrons and photons interact. Whenever they tried to calculate certain quantities, like the way an electron's charge or mass are modified by its own electromagnetic field, the answers blew up to infinity. Infinite self-energies, infinite corrections, not a little too big, literally unbounded. It was as if the math were saying, beneath the simple picture of a charged particle in empty space, there is an ocean of activity so violent that naive calculations drown in it. At first, this looked like a sign that the theory was flawed. Infinities feel like a breakdown, not a feature. But a few people, including Hans Bethe, Julian Schwinger, Richard Feynman, and Shinichiro Tominaga, began to understand that there was another way to see it. Instead of treating the infinities as physical quantities, they learned to reinterpret them as artifacts of how they were describing the system. You could, in a carefully defined way, separate the infinite parts and absorb them into redefined, finite parameters like the observed mass and charge. The process became known as renormalization. Ugly word, powerful idea. What matters for us is not the technical details, but what those infinities hinted at. The vacuum, in the quantum field view, is not empty. It is seething. Virtual particles flicker in and out of existence. Fields fluctuate even in their lowest energy configuration. When an electron sits in what looks like empty space, it is surrounded by a cloud of these fluctuations, polarizing the vacuum around it. That cloud alters its behavior. It shifts the energy levels of atoms, producing tiny corrections that can be measured as the Lamb shift in hydrogen. So the infinities were not just a nuisance. They were a symptom of the fact that what we call nothing is phenomenally busy. To see what a quantum field is in simpler terms, imagine that instead of thinking of particles as little marbles flying around, you think of them as ripples on a universal medium. But now, instead of water filling only a pond, the medium fills all of space. For each type of particle, there is a corresponding field that extends everywhere. The electron field, the photon field, the quark fields. At every point in space, each field has a value. When you see an electron in your detector, what you are really seeing is a localized excitation, a ripple of the electron field. The vacuum state, in this language, is the configuration in which there are no real particles present. No excitations that can propagate out and be measured directly. But because of the uncertainty built into quantum mechanics, the fields cannot be perfectly flat. They must jiggle, they must fluctuate. Those fluctuations carry energy. This is often called zero-point energy, the energy that remains when you have taken away everything you can. This sounds abstract, almost like a philosophical flourish, but it has concrete, measurable consequences. In the late 1940s, the Dutch physicist Hendrik Casimir considered what would happen if you placed two uncharged, perfectly conducting metal plates very close together in a vacuum. Intuitively, you might expect nothing remarkable. No air between them, no charges, just stillness. Quantum field theory suggests otherwise. The presence of the plates restricts which electromagnetic modes can exist between them. You can think of it loosely as limiting which vacuum fluctuations fit in the gap. Outside the plates, the full spectrum of modes persists. The result is a tiny difference in vacuum energy between the inside region and the outside region. That difference produces a force, pushing the plates together. This is the Casimir effect. Not a magic trick, not a metaphor. A real force, arising with no charges, no fields deliberately applied, only from the way the quantum vacuum responds to boundaries. Experiments in later decades measured this force. You can set up two carefully polished plates, or a plate and a sphere, bring them within microscopic distances, and detect the small attraction. Those measurements are difficult and sensitive, but they agree with the predictions. So here, in a laboratory, we have a quiet but radical message. Even in an evacuated chamber, stripped of air, shielded from stray fields as much as possible, there is still something that can push. Nothing, once again, refuses to be nothing. Another line of evidence arrives from the sky. In the mid-1960s, Arno Penzias and Robert Wilson were working with a radio antenna in New Jersey, trying to measure faint signals. They kept picking up a persistent background noise, a hiss that seemed to come from every direction. They tried everything they could think of to get rid of it. They even cleared out nesting pigeons and cleaned away their droppings, suspecting contamination. The noise remained. They had stumbled upon the cosmic microwave background, the afterglow of the hot, dense, early universe, stretched into microwaves by billions of years of expansion. That nearly uniform radiation filling space is not exactly the quantum vacuum, but it reinforces a broader lesson. What we might casually call empty space can carry imprints of past events, relic radiation, structure. Taken together, these threads begin to tug our intuition in a new direction. The vacuum is not an empty box waiting to be filled. It is a particular state of a set of fields. That state has energy. It can interact with matter. It can respond to boundaries. It can carry the memory of the universe's history in the form of background radiation. And as we will see, it can influence the expansion of the cosmos itself. To make this more visceral, imagine standing alone in a silent room late at night. The air is still. The lights are off. You might describe it as empty, a neutral container. But you know, if you think about it, that the room is full of invisible signals. Wi-Fi, radio broadcasts, the faint hum of electrical fields from wiring in the walls. There is a dense web of activity you do not feel directly, but your devices do. The quantum vacuum is like that, and then some. Not just signals layered on top of emptiness, but the baseline itself, humming. The existential twist is subtle. We often comfort ourselves with the idea that if you strip away all the chaos of life, you will reach something simple, pure, quiet. In physics, for a time, the vacuum seemed like that. No particles, no forces acting, just nothing. But the deeper picture says, beneath the complexity is not calm, but a more fundamental kind of complexity. An order that never fully shuts off. It is here that the idea of an energy landscape starts to take shape in a more literal way. Each field has a potential, a relationship between its value and its energy. The vacuum corresponds to a configuration where all fields sit in some combination of minima in their potentials. But those minima need not be absolute. There can be multiple valleys of different depths. The vacuum is then not just no particles, but the fields arranged in a particular pattern that gives the lowest accessible energy. We know Mose-Crosser. When we ask whether the universe is stable or metastable, we are really asking about the shape of that combined landscape. Is the valley we inhabit the deepest possible? Or could there be others, lower and different, separated by barriers that quantum tunneling could, in principle, overcome? The quantum vacuum, pouring into our understanding through calculations of Lamb shifts and Casimir forces, is the stage on which that question is focused. And notice something else. Once you accept that the vacuum has energy, you have to ask how that energy interacts with gravity. In Einstein's general relativity, energy and momentum curve space-time. If the vacuum has a certain energy density, it should act like a sort of fluid filling space, gravitating in a specific way. Under certain conditions, that can produce a repulsive effect, driving accelerated expansion. The term that encodes this in the equations is the cosmological constant. So the same vacuum that shows up as a jitter in atomic levels, as a slight push between plates, also shows up, if you take the theory seriously, as a candidate for the mysterious dark energy that seems to be pushing galaxies apart faster and faster. The tiny zero-point energies of countless modes of countless fields add up, in naive calculations, to a vacuum energy density that is unimaginably larger than what cosmological observations infer. This mismatch, famously enormous, is sometimes called the worst prediction in physics. Again, the technical details are less important here than the attitude shift they force. We started with an ether, a material medium imagined to comfort our wave-trained intuition. We killed it when experiments demanded we do so. We then accepted fields and a vacuum state that is anything but empty. That vacuum, when treated with the same seriousness we apply to matter, offers both small laboratory effects and a possible explanation for the larger-scale behavior of the universe. And yet, our attempts to compute its energy clash violently with what the sky tells us. At every step, nothing resists being tamed into a simple concept. It is as if the universe is reminding us that our craving for emptiness as a neutral baseline is a projection, not a feature. There is a quiet, almost uncomfortable beauty in this. You sitting here, breathing, listening, are an arrangement of excitations on top of a vacuum that is itself an arrangement. Your atoms owe their stability to the way fields settle into particular patterns. Your chemistry exists because the vacuum chose, or fell into, a specific configuration in the early universe. Even sleep, even silence, are built on this restless foundation. It is natural, in the face of this, to ask, if the vacuum can influence how atoms behave, if it can push plates together, if it can, in principle, drive cosmic expansion, what else can it do? Could it, under different conditions, adopt a different value, a different pattern? If so, what would that mean for everything built on top of it? Those questions lead us toward the notion of phase transitions in the universe. Just as water can be liquid, solid, or gas, with different properties in each state, the vacuum itself can come in different phases, with different field values and different effective laws. Our universe has already passed through such phases in its early history. At each transition, what it meant to be a particle, a force, a stable structure, changed. Knowing that, it becomes a little easier and a lot more unsettling to imagine that the vacuum we live in now might not be the final one. That nothing, in its current form, might be only one chapter in a longer story of shifting ground states. That the question is not just what the vacuum is, but how it came to be this way, and how long it can stay here. For now, the quantum vacuum sits in the background of your daily life as an invisible participant. It sets the canvas on which your body and mind arise. You never see it directly, but it touches you constantly, like the faint hiss in Penzias and Wilson's antenna, like the tiny pull in Casimir's plates. It is a quiet, persistent reminder that the universe's most basic layer is not a blank, but a dynamic system. And once you see it that way, the next step almost suggests itself. If the vacuum is a configuration in an energy landscape, then the question of stability is not just, are we in the lowest valley? But what are the possible paths from here to anywhere else? You can think of those paths like roads you cannot see, laid out in an invisible landscape, while you walk confidently on a single, familiar street. For most of human history, we had no reason to suspect that the landscape itself might be in motion. The stars rose and set, the constellations seemed fixed, even when telescopes showed that some of those stars were actually spiral nebulae, small swirling patches of light. The scale still felt static. The universe was a big room, filled with stuff, sitting there. Then, in the early decades of the 20th century, evidence began to whisper that the room was stretching. By carefully measuring the light from distant galaxies and noticing how it was shifted toward the red end of the spectrum, astronomers inferred that most galaxies are moving away from us. The farther a galaxy is, the faster it appears to recede. This pattern became known as the expansion of the universe. Space itself is stretching, carrying galaxies apart like raisins embedded in rising dough. At first, many people expected that this expansion would slow down over time. Gravity pulls things together. The combined mass of all the matter in the universe should act as a brake, gradually decelerating the initial outward rush. The question was whether the universe would expand forever, more and more slowly, or eventually halt and recollapse in a big crunch. To answer that, you need to know how fast the universe has been expanding at different times in its history. That is not something you can measure with a single snapshot. You need cosmic distance markers that act like reliable beacons, telling you both how bright they truly are and how far away they must be to appear as faint as they do. In the late 20th century, two teams of astronomers turned to a particular kind of exploding star for help. Type 1, a supernovae. These are thermonuclear explosions of white dwarf stars in binary systems. The important thing, for cosmology, is that they are remarkably consistent in their peak brightness. Once you account for some subtle variations, that consistency makes them standard candles on cosmic scales. The Supernova Cosmology Project and the High Redshift Supernova Search Team spent years gathering data on these explosions in very distant galaxies. Each supernova's light carried information about how far its host galaxy was and how much the universe had expanded since the light was emitted. When they compared the observed brightnesses with the expectations from a decelerating universe, something did not fit. The distant supernovae were dimmer than expected, as if they were farther away than they should be in a simple slowing down scenario. The most straightforward interpretation was unsettling. The expansion of the universe is not just continuing, it is speeding up. Instead of gravity winning, some other effect appears to be counteracting it on large scales, pushing space to expand faster and faster with time. This discovery, announced in the late 1990s, would later earn a Nobel Prize. It introduced a new phrase into cosmology's everyday vocabulary: dark energy. Dark energy is a placeholder name. It tells you more about our ignorance than about the thing itself. Dark, because it does not emit or absorb light. Energy, because it behaves, in Einstein's equations, like a uniform energy density filling space, exerting a kind of negative pressure that accelerates expansion. One simple way to model dark energy is to revive a term Einstein himself once introduced and then discarded: the cosmological constant. In general relativity, the cosmological constant is a term you can add to the equations that acts like a constant energy density of the vacuum. If this constant is positive and not too large, it makes the universe's expansion accelerate. In this picture, the vacuum is not just a restless, fluctuating quantum state. It also has a fixed energy density that, on average, pushes the fabric of space-time apart. At first, this looks almost elegant. We already know, from quantum field theory, that the vacuum should carry zero-point energy. We know from Casimir-type effects that this energy can have physical consequences. So, perhaps dark energy is simply the gravitational imprint of vacuum energy. The cosmological constant is just the vacuum's average energy density, showing up on cosmic scales. Then you do the calculation. If you take the quantum fields we know about, sum up their zero-point energies up to some high-energy cutoff, and treat that sum as the vacuum energy density, you get an answer that is absurdly large. The ratio between the naive theoretical value and the tiny value inferred from cosmological observations is sometimes described as 10 to the power of 120, perhaps the worst mismatch between theory and experiment in all of physics. To get a sense of the scale, imagine that your bank's computer system insists with complete confidence that your account balance is a number with 120 zeros after it, while your printed statement shows a modest single-digit amount. You might reasonably suspect that the way you are doing the calculation is wrong. Cosmologists, looking at this vacuum energy problem, find themselves in a similar position. The universe, as measured through supernovae, cosmic microwave background fluctuations, and large-scale structure, suggests a small but non-zero dark energy density that dominates the energy budget today. Roughly speaking, about 2/3 of the total energy content of the current universe appears to be in this dark energy form, with about 1/4 in dark matter and a small fraction in ordinary matter. Quantum field theory, as naively applied, insists that the vacuum energy should either be enormous or, if some miracle of cancellation occurs, exactly zero. Neither fits. This is what people mean when they call it the worst prediction. It is not that the equations are randomly wrong, they work brilliantly for many other things. It is that, when you extend a framework that has been extraordinarily successful at small scales to the largest possible scale, and ask it a seemingly straightforward question, what is the energy of the vacuum? It gives you an answer that reality calmly contradicts by a ludicrous margin. One way to respond is to imagine that there is some as-yet unknown mechanism that cancels almost all of the vacuum energy, leaving a tiny residue that we observe as dark energy. Another is to treat the cosmological constant as a bare parameter to be measured, not derived, and accept that its small value is a fact we do not yet explain. More speculative ideas go further. Perhaps dark energy is not a true constant, but a slowly varying field, sometimes called quintessence, whose energy density changes over time. Perhaps, in even more exotic scenarios, the vacuum energy becomes more negative with time, leading to a future Big Rip, in which the accelerated expansion eventually tears apart galaxies, stars, planets, and even atoms. It is important to say, clearly, that many of these boundary case scenarios are speculative. Observations so far are consistent with a cosmological constant, like dark energy, that remains roughly constant in density as the universe expands. That picture leads to a future in which galaxies outside our local group eventually drift beyond our cosmic horizon, leaving an increasingly cold, sparse universe in the very long term. From the point of view of our lives, nothing in that is urgent. The timescales are vast beyond our imagining. The acceleration does not change the way apples fall or how galaxies behave on human timescales. It is a background condition. But the existential weight of the discovery is not about immediacy. It is about what it says regarding our assumptions. We used to imagine the vacuum as a neutral stage. Then we learned that it has quantum fluctuations. Now we have strong evidence that, in addition, the vacuum or something that behaves very much like it has an average energy density that can shape the entire history and fate of the cosmos. The stage, in other words, is acting. When you look at diagrams of the universe's expansion history, you see a line that curves. Early on, in the hot, dense past, radiation and matter dominated. Their gravity slowed the expansion. As the universe grew and thinned, the dilution of matter made its influence weaken. At some point, the persistent, roughly constant energy density of dark energy began to dominate, causing the expansion to accelerate. That curve is not just a mathematical toy, it is a summary of how the vacuum and its contents have negotiated the structure of reality over billions of years. And yet, Our best microscopic theories cannot tell us why the dark energy density has the small value it seems to have. They cannot tell us whether it is truly constant or a slowly rolling field. They cannot tell us whether the worst prediction is a sign of a deeper principle we have missed, or a clue that our entire way of counting vacuum energy is misguided. There is a temptation, when confronted with this level of mismatch, to retreat into either dismissal or mysticism, to shrug and say the numbers are what they are, or to treat dark energy as some enigmatic substance beyond reason. But there is another, quieter response available. To see this as a mirror. The mirror shows us how strong our craving is for the universe to be tidy, how eager we are to believe that if we have powerful equations in one domain, they can be trusted everywhere. How surprised we are when reality refuses to follow our extrapolations. Dark energy is a reminder that the vacuum is not simply a mathematical minimum, but a physical actor whose properties can be measured and whose nature remains open. It is, in that sense, an invitation to humility, and it deepens the question of stability. If the vacuum energy is tied to fields that permeate space fields like the Higgs field, then the value of those fields in the vacuum matters enormously. A slight change in that configuration, a shift in the vacuum to a different valley in the energy landscape, could alter both the behavior of matter and the large-scale expansion. The same background that quietly drives galaxies apart might be, under different conditions, part of a very different rulebook. So when we talk about vacuum metastability, about the possibility that our current vacuum is not the absolute ground state, we are not talking about an abstract risk in an otherwise neutral environment. We are talking about the potential reconfiguration of the very agent that currently steers the cosmic expansion. From the human point of view, this can sound paralyzing. If the vacuum can both support the structures we depend on and, in principle, change in ways we do not control, what are we supposed to do with that information? One answer is we cannot do very much about the vacuum. Its properties are what they are. Our influence, for now, is confined to the thin film of complexity on planetary and stellar scales. But another answer is more inward. Knowing that the vacuum has this active, mysterious role can reshape how we hold our certainties. The fact that the universe's acceleration was discovered only recently, in the last few decades, means that for almost all of human history, people lived under a picture of reality that lacked this element. They lived, loved, feared, and created inside an expanding universe, without any awareness that the expansion was speeding up. Their meanings and choices were not diminished by that ignorance. We, now, live with the opposite condition. We have an awareness, however incomplete, that the vacuum is not passive. We know that there is a component of reality we cannot directly touch, that nonetheless writes the large-scale story. That knowledge does not tell us what to value. It does not give us instructions. It does quietly erode certain illusions. The illusion that the universe is a sturdy room whose size and shape are fixed. The illusion that emptiness means irrelevance. The illusion that, given enough equations, we will finally arrive at a picture of the world that is both complete and emotionally satisfying. Dark energy sits there, in the background, like a question written into the fabric of space itself. A faint pressure that says, the vacuum is not what you thought. The laws you rely on may be the expression of a particular state, not an eternal necessity. And if that is true, then the question that began with Oppenheimer's nervous glance at the Trinity device and continued through the Higgs discovery becomes even sharper. What if the very field that gives mass to our particles, that helps define the stability of atoms and stars, is itself part of a vacuum configuration that is only holding, not guaranteed? If the vacuum is the quiet architect of expansion, then the Higgs field is the part of that architect that reaches directly into your bones. Physicists have a compact name for the set of equations that describe almost everything we can do in particle accelerators, and most of what happens in ordinary matter, the Standard Model. It sounds modest, almost boring, like a basic setting you might ignore in a menu. In reality, it is one of the most successful theories humans have ever built. You can think of it as a kind of directory for the universe at small scales. It lists basic ingredients: quarks, which clump into protons and neutrons; leptons, which include the electron and its heavier cousins; and the particles that carry forces, like photons for electromagnetism and gluons for the strong interaction. It also includes the W and Z bosons, which mediate the weak force, responsible for certain forms of radioactive decay. In this picture, most of the richness of the world comes from combinations and interactions of these building blocks. The solidity of a table, the color of a sunset, the chemistry of a living cell, all emerge from these particles, exchanging force carriers in patterns governed by the Standard Model's rules. But when the theory was being assembled in the 1960s, there was a problem that would not go away. The mathematics wanted symmetry. Symmetry, in this context, is like a rule that says the equations should not change when you make certain transformations, like rotating an abstract internal dial. Those symmetries are beautiful and powerful. They keep the theory under control. Left to themselves, they tend to favor massless particles, zipping around at the speed of light. The world clearly disagrees. Many particles have mass. The W and Z bosons, in particular, are heavy. If you simply add mass terms for them by hand, you break the symmetries that make the theory work. If you keep the symmetries and refuse to add those terms, you get elegant equations that describe a universe unlike our own. The question was simple and sharp. How do you give particles mass without ruining the symmetry that makes the theory consistent? The solution that eventually crystallized is subtle. Instead of assigning mass directly, you introduce a new field that fills all of space. A field whose presence breaks the symmetry not by vandalism but by a kind of choice. This is the Higgs field. Imagine a perfectly flat field of snow stretching off in every direction. Before anyone steps on it, the scene is symmetric. No direction is special. Then a person decides to walk in a straight line, leaving a visible path. The snow itself has not lost its underlying symmetry, but the specific state it is in now picks out a direction. The symmetries of the laws remain. The symmetries of the ground state are reduced. The Higgs field behaves a little like that. Its underlying equations possess a symmetry, but the lowest energy state of the field is not at the symmetric point. Instead, the field settles into a non-zero value everywhere. Physicists call this spontaneous symmetry breaking. In that state, other particles moving through space interact with the Higgs field in different strengths. That interaction resists their motion, giving rise to what we perceive as mass. A common analogy is a kind of cosmic fog. The Higgs field is that fog, permeating everything. Particles that couple strongly to it feel more drag and appear heavier. Those that barely interact with it, like the photon, remain massless. Your body, your chair, the air you breathe, are all made of excitations of fields that are moving through this invisible fog all the time. In the 1970s and 80s, this idea became embedded in the Standard Model. It made the equations work. It explained why the weak force carriers are heavy, while the photon is not. But there was a catch. No one had actually seen the Higgs field's quantum of excitation, the Higgs boson itself. It was like having a piece of machinery that behaves exactly as if it contains a hidden gear, but never seeing the gear directly. Over the next decades, particle physicists built machines that hurled particles at one another at ever higher energies, hoping to produce that elusive excitation. At CERN, the Large Electron Positron Collider, LEP, pushed close to the energies where a Higgs boson could appear, but did not quite reach it. At Fermilab, the Tevatron accelerator smashed protons and antiprotons together, searching in crowded collision debris for hints. There were tantalizing suggestions, but no clear discovery. As the years went on, the absence of the Higgs became more than an experimental frustration. It became a philosophical pressure point. If the Higgs did not exist, the Standard Model's mechanism for mass would fail. Some alternative would be needed, something even stranger. The stakes were high enough that nations agreed to cooperate on an unprecedented project, the Large Hadron Collider. The LHC is a ring of magnets and detectors buried beneath the border between France and Switzerland, stretching for tens of kilometers. Its job is simple in concept and immense in execution. Accelerate protons to energies far beyond anything previously achieved. Smash them together and read the spray. From those sprays, using careful statistics and intricate detectors, physicists reconstruct what must have been there in the first instance of collision. On a July day in the early 21st century, the big experiments at the LHC Atlas and CMS announced that they had found something new. In their data, a bump appeared in the distribution of events, a sign that a new particle with a mass around 125 giga-electron volts was being produced and decaying. Its properties, within errors, matched those expected for the Higgs boson. It was real. Outside the field, the discovery was often wrapped in phrases designed to attract attention. The God particle, the final piece of the puzzle. Inside, the feelings were more mixed and more interesting. On one level, the Higgs existence confirmed that the broad picture of the Standard Model was correct at the energies accessible to the LHC. The fog is real. The way particles acquire mass through their interaction with that fog is real. That alone is astonishing. On another level, the specific mass of the Higgs boson opened doors to deeper questions. When you plug that mass, along with quantities like the mass of the top quark, into the equations that describe how the Higgs field's potential evolves at very high energies, you get an answer that is far from trivial. The Higgs potential is often drawn with a distinctive shape, like a sombrero hat. At the center, the energy is high. Around the rim, there is a valley where the field can settle. Our vacuum corresponds to the field sitting at some point on that rim with a non-zero value. But this picture is only a slice at low energies, a kind of shadow. At very high energies, quantum corrections can tilt, stretch, or reshape the potential. When theorists accounted for those corrections, using the measured Higgs mass, something delicate appeared. The effective potential seemed to dip slightly lower at very high field values, creating the possibility of another minimum, a deeper valley far away in field space. In that case, our current vacuum would not be the absolute lowest energy state. It would be a local minimum, stable against small perturbations, but not fundamentally final. A metastable state. The calculations suggested that, given the Higgs and top masses as measured, the Standard Model sits near the boundary between absolute stability and metastability, not clearly safe, not clearly doomed, but balanced close to a critical line in parameter space. Small shifts in those masses, within experimental uncertainties, can move us from one side of the boundary to the other. This is where the language of glue becomes more than metaphor. The Higgs field, with its quiet, uniform presence, helps bind the rules of the visible world together. It sets the masses of fundamental particles. Those masses, in turn, influence the structure of atoms, the behavior of stars, the rates at which certain reactions proceed inside the Sun and in supernovae. If you change the Higgs field's value significantly, the web of relationships binding the cosmos's familiar structures would be torn and rewoven in a different pattern. From an everyday perspective, that glue feels unbreakable. Your body does not randomly lose its mass. Tables do not spontaneously become transparent because electrons decided to ignore the Higgs. The stability is so complete that you forget it is something that can even be questioned. Metastability brings that question back with a different tone. It does not say that the glue is about to fail. The predicted lifetime of a metastable Higgs vacuum, if the Standard Model holds all the way up to extremely high energies, is often estimated to be staggeringly longer than the current age of the universe. Longer than stars will burn. Longer than galaxies will shine. For all practical purposes, on human timescales, it might as well be eternal. But it is not eternal in principle. It is only statistically long-lived. In the space of possibilities, there exists another valley where the Higgs field takes a different value, and the universe would be different. Our valley is a deep dent, not the basement. Emotionally, this is strange territory. Most of our language around safety and danger, around permanence and change, is built on shorter timescales. We know how to feel about a storm passing overhead, or a civilization lasting centuries, or a species facing extinction over millennia. We do not have an instinctive emotional register for changes that might occur over time so long that no human culture could possibly witness them. What metastability asks us to do is to decouple immediate risk from deep ontology. It says, you are not in danger from this, not in the way you are from climate change or asteroids or your own technology. But the universe's rulebook may not be underwritten by a mathematically necessary, unchangeable foundation. It may be sitting in a particular configuration of a field that could, in principle, change. There is another layer to this, one that rarely appears in popular discussions. The standard model, successful as it is incomplete. It does not include gravity in a quantum way. It does not explain dark matter. It does not account for neutrino masses in their full detail. It has many parameters that must be chosen by hand. When physicists talk about the Higgs potential and vacuum stability, they usually do so within the standard model extended up to scales far beyond what we can test. That is a bold extrapolation. New physics beyond the standard model could change the picture. Additional fields, new interactions, heavy particles not yet discovered, all of these could alter the running of couplings, the shape of the Higgs potential, and hence the distinction between stable and metastable. Some theories introduce mechanisms that stabilize the vacuum automatically. Others make it less stable. In that sense, our current conclusion about metastability is provisional, living at the boundary between what we know and what we suspect. Still, the fact remains. With the Higgs mass we have measured, and within the simplest extension of what we trust, the universe looks finely balanced. The glue holding its structure is real, mathematically encoded, experimentally supported, and at the same time, the field providing that glue is perched in a way that invites questions rather than silencing them. You can feel this if you sit with it, in your everyday surroundings. Pick up an object near you. A cup, a book, a phone glowing in your hand. Its weight, the sense of heft you get when you lift it, comes from the masses of its constituent particles. That mass is not a given. It is a relationship, mediated by the Higgs field, between those particles and the vacuum's configuration. The stability of that relationship, your confidence that the object will still exist tomorrow with the same weight, is rooted in the assumption that the Higgs field's value will not suddenly change. Common sense tells you that assumption is safe. The physics, in its careful, dry way, says, so far as we can tell, you are right on any timescale that matters to you. But it also whispers, and yet, at a deeper level, this safety is not an absolute law. It is a property of a particular state of a field, a state that might be one among many in an abstract energy landscape. The Higgs discovery did not just complete a theory. It pulled a curtain back to reveal that one of the central pillars of reality, the existence of mass, rests on a global condition that might not be the only option. Once you see that, it becomes harder to think of the universe as something built out of unshakable bricks. It looks more like an intricate pattern held together by tension and balance, sensitive to the underlying state of fields you will never touch directly. And that is the quiet, unsettling beauty of it. The glue that makes you possible is, itself, a question. Questions like that do not just sit in your head. They lean on you, the way a heavy building presses into its foundations, making you wonder what kind of ground could carry so much weight for so long. To see what that ground might look like, you have to imagine something you will never see directly. The shape of an energy landscape drawn not in the hills outside your window, but in the space of possible values of a field. The Higgs field, in particular, has a potential energy that depends on what value the field takes. If you could somehow plot that dependence and walk through it, you would find yourself in a landscape with a very particular silhouette. Physicists like to describe it as a sombrero. Picture a wide, circular hat with a raised crown in the middle and a brim that dips lower all the way around. If you slice that hat through the middle and look at the cross-section, you see a peak at the center and a valley around it. Before the Higgs field settles, the symmetric point where the field value is 0 is like the top of that central peak. As the universe cools and the field rolls down, it does not come to rest at the top. It slides off, down the slope, and ends up somewhere on the ring of the valley, at some non-zero value. That choice, that settling into the brim, breaks the symmetry in a way that gives particles mass. In this picture, our vacuum is the state where the Higgs field has chosen a particular point on that ring. All around us, in every direction, the field has that same value. It is not something you can turn off by walking to a different place. It is a property of the entire vacuum. If that were the whole story, the vacuum would look simple again. The sombrero potential would be a neat cartoon, a central hump, a surrounding valley, our field sitting calmly at the bottom of that valley. True vacuum. Absolute minimum. End of conversation. But the universe is more complicated than a cartoon. When you include quantum corrections, subtle shifts in the potential caused by virtual particles and interactions at high energies, the sombrero can warp. The exact shape depends on the masses and couplings of particles, especially heavy ones, like the top quark. When theorists put in the values we have measured, the brim of the hat does something delicate. At very large field values, far away from the valley where we live, the effective potential appears to bend downward again, forming a deeper minimum. If that is true, then our current state is not the deepest valley. It is a local minimum, a place where the field can sit comfortably for a very long time, but not forever in principle. A false vacuum. The term false vacuum sounds dramatic, but it has a precise meaning. A true vacuum is the lowest possible energy state of a field. If you disturb it slightly and let go, it simply returns to the same state. A false vacuum is a configuration that looks stable to small nudges, but is not the global minimum. It is like a marble resting in a small dimple on the side of a mountain. Push it gently, and it rolls back. But if, by some rare fluctuation, it gains enough energy to crest the rim of the dimple, it can roll down the mountain toward a deeper hollow. In quantum field theory, the marble does not need to be kicked over the barrier. It can tunnel. Quantum tunneling is a process where a system transitions through a barrier that it would not have the energy to climb classically. For a field in a false vacuum, tunneling translates into the possibility of nucleating a bubble of true vacuum somewhere, a tiny region where the field has slipped into the lower energy valley. The important thing is not the image of a bubble itself, but what it implies. If our vacuum is false, the rules we experience are tied to a particular field value that is not guaranteed forever. There exists, somewhere in the abstract space of possibilities, another configuration where the Higgs field takes a different value and the energy is lower. Physicists convert this into diagrams. On one axis, they plot the mass of the Higgs boson. On another, the mass of the top quark. Using the equations of the Standard Model, they carve this plane into regions: stable, metastable, unstable. The measured values seem to fall in or near the metastable region. That is, according to these calculations, our vacuum looks long-lived, but not absolutely secure. These diagrams are not photographs of reality. They are maps drawn from an extrapolation of a theory beyond the energies we have explored. New physics could redraw the borders. More precise measurements could shift our point on the map. Some analyses place us a little deeper into the metastable zone. Others nudge us closer to stability. But the overall message persists. The numbers we have found do not scream true vacuum. They whisper, delicately balanced. The ball, in a valley analogy, helps here, but it can also mislead. In the cartoon, there is a clear picture of height, slope, and direction. In the real field space, the potential is a function defined over high-dimensional configurations. Tunneling is not a ball rolling. It is a change in the field's configuration in a region of space, governed by quantum amplitudes. The energy barrier between our vacuum and the hypothetical deeper one could be enormous, making the tunneling probability per unit volume staggeringly small. That is why the estimated lifetime of a metastable vacuum can be so long that it dwarfs every timescale we care about. Still, the idea that there is a lower valley is enough to alter the philosophical temperature of the room. There is a particular flavor of comfort in believing that the universe is in its ground state. It says, whatever else changes, the underlying configuration of fields is as stable as it can be. No surprise phase transitions lie ahead. The rules are permanent. Even if stars die and galaxies fade, the vacuum remains what it is, indifferent but secure. A false vacuum takes that away. It replaces the idea of absolute permanence with an idea of prolonged, conditional holding. The field sits in a valley that is deep enough to be effectively stable over eons, but not unconditionally favored. There is always another possibility encoded in the same equations. You can feel the echoes of this in human systems. Societies settle into patterns that look stable. Institutions endure for generations. Economies, laws, power structures all seem natural, as if they could not have been otherwise. Underneath, tensions accumulate. Small disturbances are absorbed. The system returns to a familiar configuration over and over, reinforcing the feeling that it is permanent. Then, occasionally, a threshold is crossed. A crisis, a technological shift, a slow build-up of contradictions reaches a point where the social field reconfigures. Revolutions, collapses, sudden changes in order. What looked stable was metastable. A false vacuum of culture, held in place until a barrier was breached. In that sense, vacuum metastability is not a foreign idea. It is a more extreme, cosmic version of patterns we already know. The unsettling part is that, in this case, the society is not a government, but the set of physical laws we depend on. Popular stories have sensed this unease. In the graphic novel Watchmen, the world exists under the constant threat of nuclear annihilation. The apparent peace is a brittle equilibrium, maintained by deterrence and deception. Dr. Manhattan, the blue, godlike figure who experiences time all at once, moves through events with a kind of detached awareness. He knows that the apparent stability of the world is contingent, that everything is suspended over potential catastrophe. The emotional tone of that work is metastability made human. A world that feels stable, while everyone knows, consciously or not, that the stability is conditional. Our universe, under the false vacuum view, is like that but more impersonal. There is no villain pressing a button, no moral drama about whether someone will choose destruction. The very background we live in is a state that, according to the equations, is not the absolute bottom. If a transition happened, it would not be because of a decision. It would be because of the probabilistic structure of quantum fields. This is where the imagination often jumps ahead to the bubble picture. If a tiny region of space were to undergo a transition to the lower energy vacuum, it would form a bubble of true vacuum. Inside that bubble, the Higgs field would have a different value. The masses of particles, the strengths of forces, the rules of chemistry could all change. The interface between the old vacuum and the new would have enormous energy. The bubble wall would accelerate, expanding outward at nearly the speed of light. From the perspective of someone in the old vacuum, there would be no warning. One moment, the local rules hold. The next, the bubble wall passes, and everything that was is redefined or erased. There is no outrunning a front that moves at light speed. No shelter to be had in physics, built for the old vacuum. This is a terrifying scenario if you focus on it as an impending event. But the physics we have suggests that if our vacuum is metastable, its lifetime is fantastically long. The chance that such a bubble would form within our observable universe in the next span of time comparable to its current age is effectively zero. The calculation that tells you the vacuum is metastable is, at the same time, a calculation that tells you the risk is remote beyond caring. So why does the idea stick in the mind? Because it reframes what kind of security the universe offers. It says, your world is not built on an absolutely rigid foundation. It is built on a plateau, carved in a landscape that extends beyond your view. You are not in a state that must exist. You are in a state that happens to exist, long enough for beings like you to arise and wonder about it. This realization can push you in different directions. You might feel a kind of vertigo, if even the vacuum is a question. What can be trusted? If the Higgs field's value is contingent, does that make everything less meaningful? More arbitrary? Or you might feel something quieter. A recognition that you have always lived in metastable conditions, just at different levels. Your body is a metastable pattern of biology, held together by processes that will eventually fail. Your society is a metastable arrangement of power. Your planet's climate, your star's fusion, your galaxy's structure, all of these are finite chapters. The vacuum's metastability simply extends that pattern to the deepest level we currently understand. In that view, the false in false vacuum is not an accusation. It is a reminder that what we experience as solid is a pause in a larger story, a local arrangement of fields in an energy landscape that has other chapters, whether or not they ever get written within our causal horizon. The psychologists of the future may have words for the way this understanding sits alongside daily life. For now, we can only describe it indirectly. You go to work. You cook a meal. You listen to someone laugh. Somewhere in the back of your mind, if you have followed this story, there is also the knowledge that your very ability to stand and speak is tied to a global configuration of a field that may be long-lived but not mathematically sacred. That knowledge does not demand despair. It does not require fear. It asks for a shift in tone. Instead of saying, "The universe is stable, therefore we are safe," you might say, "The universe is holding, for now, in a state that allows us to exist." Instead of imagining laws as tablets carved once and for all, you might imagine them as the local bylaws of a particular vacuum, durable yet not unalterable. And somewhere beyond our current theories, beyond the sombrero and the stability diagrams, there may be other fields, other potentials, other vacua. The energy landscape could be vastly more complicated than the slice we have drawn around the Higgs. If that is the case, then our false vacuum is not an exception. It is one configuration in a sea of possibilities. A small dent on a slope that stretches far beyond what we can currently see. Once you start imagining all those other valleys, even as abstractions, a part of you cannot help asking the impolite question: what would it actually mean if the field ever decided to move? In the language of quantum field theory, that question becomes one about vacuum decay. Not decay in the sense of rotting or crumbling, but in the sense of a transition from one state to another. A metastable vacuum can, in principle, decay into a lower energy, more stable vacuum through a process that is at once deeply mathematical and eerily simple to describe. It begins nowhere in particular. In a false vacuum, the field is stuck in a local minimum, separated by an energy barrier from the true minimum. Classically, it would stay there forever. But quantum mechanics allows for tunneling. The field can borrow the possibility of being on the other side of the barrier in a small region of space, even if it does not have the classical energy to climb over. That tunneling event nucleates a bubble of true vacuum. Inside the bubble, the field takes the lower energy value. Outside, the universe is still in the false vacuum. The boundary between them, the bubble wall, contains a lot of energy. The pressure difference between the higher energy outside and the lower energy inside makes the bubble expand. In the simplest cases, that expansion quickly accelerates to almost the speed of light. From the inside, you would never notice the bubble forming, because your concept of inside depends on the vacuum you are in. From the outside, if you could somehow see it from a safe distance, you would see a sphere of new vacuum consuming the old, its edge racing outward. But there is no safe distance, not in any conventional sense, because nothing can outrun a front that moves at light speed. There is no warning that can arrive before the event itself. This is the origin of the darkly playful term big slurp. Instead of a big crunch or a big rip, the vacuum could, in principle, end in a sudden slurp into a lower energy state, rewriting the rules as it goes. The key word, though, is in principle. In principle, VT Nation. When people like Sidney Coleman and Frank DeLucia worked out the theory of vacuum decay with gravity included, they found that the rate of such tunneling events depends sensitively on the height and width of the barrier between vacua and on the difference in energy between them. For a potential like the Higgs, with parameters close to the ones we measure, that rate appears to be extraordinarily tiny. You can translate it into an expected lifetime for our vacuum that comes out as something like an exponential of an enormous number, a timescale so long that writing it out as ordinary years is almost meaningless. If you compare that lifetime to the current age of the universe, the age comes out like a fraction, with one in the numerator and a denominator so vast it barely deserves the name fraction. From a human or even stellar perspective, the vacuum might as well be eternal. This is why serious physicists, when they talk about vacuum decay, do so with a careful tone. The scenario is a logical consequence of the theory under certain assumptions about the Higgs potential and the absence of stabilizing new physics. It is not a prediction of imminent doom. It is one branch on a conceptual tree. But thought experiments have their own power, and this one is hard to ignore. Imagine, just as a picture, that such a bubble did appear somewhere in the universe. It could be at unimaginable distance from us. It could be microscopic in its initial size. It does not matter. As it expands, the conditions inside differ qualitatively from the ones outside. Particle masses could change. Charges could change. The very notion of what counts as a particle might change. Atoms as we know them might not exist. The constants that allowed stars and chemistry to arise might be replaced by a set that allows nothing familiar. Or perhaps a very different form of structure. From our standpoint, this is not an apocalypse in the usual sense. It is not destruction. With us left to pick through ruins, it is the end of our branch of physics. A clean edit of the cosmic rulebook. Popular culture occasionally brushes up against this idea. In the film Avengers: Infinity War, a character snaps his fingers and half of all life in the universe disintegrates into dust. It is presented as an almost aesthetic gesture, instantaneous, impartial, obeying a numerical rule rather than personal vendetta. The emotional impact comes from the sense that the universe's order has been arbitrarily violated by a being who can rewrite the terms. Vacuum decay, if it happened, would be far colder. No intention, no pattern spared or selected. It would not kill half of life. It would change the conditions that make any life possible under our current definitions. If that sounds like the most chilling hypothesis imaginable, it is useful to remember two things. First, the calculations that even allow us to talk about this scenario are themselves extraordinary achievements of human thought. They rely on quantum field theory, renormalization, general relativity, and precise measurements of particle properties. They are not horror stories made up in the dark. They are byproducts of taking our theories seriously. Second, every step of those calculations comes with assumptions. We extend the standard model far beyond tested energies. We ignore unknown new physics. We treat gravity in a semi-classical way, rather than a full quantum gravity theory we do not yet have. We assume that no hidden stabilizing mechanism kicks in at very high scales. Any of those assumptions could be wrong. New particles, new interactions, new principles could make the Higgs potential truly stable after all, or unstable in a way that changes the narrative. So the Big Slurp is not a scheduled event. It is a theoretical possibility emerging from a specific set of extrapolations. That raises a quieter, more interesting question. If the practical risk is so small, it might as well be zero. Why does this possibility affect us emotionally at all? One answer is that it reveals just how conditional our existence is on global, invisible facts. Your entire body, every book you have read, every memory you have, is built on assumptions about the Higgs field's value and the vacuum state that you did not know you were making. To learn that those assumptions describe a metastable configuration rather than an absolute minimum is like learning that the building you live in was constructed on a shelf of rock hanging over a void. The shelf is thick. It has lasted longer than any human life. It is expected to last for a duration that makes human history look like a flicker. And yet, it is not bedrock. Another answer has to do with our relationship to risk and knowledge. On July 16th, 1945, the physicists at Trinity debated whether their nuclear device might ignite the atmosphere. Calculations suggested that the risk was effectively zero, but the data was sparse, the theory young. They pressed the button anyway. The atmosphere did not burn. The risk, in retrospect, looks small. But the act of confronting that risk left a cultural mark. It showed that we are willing to gamble with global conditions when our understanding feels strong enough and our motives urgent enough. Vacuum decay replays that drama in a different key. This time, the risk is not something we create. It is baked into the structure of the theory. We did not choose metastability. We discovered it as a possible classification of our vacuum. We are not deciding whether to press a button. We are living in a universe whose background may be, in the technical sense, only locally stable. Yet, the emotional echo is similar. Once again, we find ourselves holding knowledge that touches on the possibility of global change beyond our control. Once again, the numbers say, not now, not for inconceivable spans of time. Once again, the act of understanding leaves us with a different feeling about how secure our world really is. There is a way to respond to this that leans into dread. You can fixate on the bubble, on the thought of a sudden wall sweeping through the galaxy. You can let that image colonize your sense of the future, but you can also take a different stance, one closer to how physicists actually live with these ideas. For them, metastability is less a countdown and more a probe. It hints at physics beyond what we know. It points to a region of parameter space where the standard model, extended naively, places us near a boundary. That near criticality might be a coincidence, or it might be a clue that some deeper mechanism prefers vacua like ours. Some proposals suggest that the universe may naturally evolve towards such critical points, balancing on the edge between phases as if they were attractors. In that view, the fact that a big slurp is even a meaningful phrase tells you that your theories have reached a certain maturity. You can talk not just about particles and forces, but about the global structure of field configurations and their possible histories. You can model what would happen if the ground state changed. You can place your own vacuum in a taxonomy of states. If the imagined bubble is unsettling, it is also a kind of compliment to human curiosity. We have, after all, moved from worrying about whether fire will burn the sky to asking whether the sky itself is in a temporary phase. And so, the chilling hypothesis becomes less about fear of an event and more about the reframing of our expectations. We no longer assume that there is a single, final vacuum. We entertain landscapes. We no longer assume that the cosmological constant is something we can derive straightforwardly from zero-point energies. We accept that the worst prediction in physics may be telling us something profound about how we count. We no longer assume that the Higgs field's role is simply to give mass. We now see its potential as a map with multiple valleys and ridges. Somewhere, behind the technical papers and the diagrams, this has an emotional consequence. It says, there is no cosmic promise that the rules you grew up with are written in an unchangeable language. There is only a long, quiet holding pattern in which those rules have remained consistent long enough for galaxies, planets, life, and minds to emerge. It is enough. It has to be. And if that holding pattern is, in the deep theoretical sense, a metastable state with a fantastically long lifetime, then the task is not to fear its end. The task is to understand what it means to live meaningfully inside something that was never guaranteed in the first place. At some point, the idea that everything is only temporarily held stops feeling like a threat and starts feeling like the water you swim in. The question then shifts. If the foundations are conditional, why are the people who understand this most deeply not walking around in a state of quiet terror? Part of the answer lives in the strange relationship between probability and time. When physicists estimate the lifetime of a metastable vacuum, they are not imagining a clock counting down to a specific date. They are calculating a rate, a probability per unit volume per unit time that a tunneling event will occur. For a Higgs-like potential with parameters close to those we have measured, that rate comes out so small that the associated lifetime is not just longer than the current age of the universe, it is longer than almost any physically meaningful timescale you can write down. Put differently, if you zoom into human history, or even the history of stars and galaxies, the chance that vacuum decay will occur in that window is, for all practical purposes, 0. The probability is there, in the equations, but spread so thinly over such immense expanses of space and time that it dissolves. Humans are not good at feeling this kind of number. Our intuition is tuned to risks like storms, illnesses, economic crashes. We understand, in our bones, what it means to say that something might happen next year, or within a lifetime, or over the span of a civilization. We do not have an instinctive sense of what it means for the expected lifetime of a state to be something like 10 raised to an absurdly large power of years. All we can honestly say is, that is not our problem. So the first reason no one seriously panics is simple. The math that makes metastability plausible also makes it irrelevant on human timescales. There is a second reason, just as important. The conclusion that our vacuum is metastable rests on extrapolating the standard model far beyond the energies we have tested. We take a theory that works astonishingly well, up to scales probed by our largest colliders, and we extend it upward by many orders of magnitude, assuming that no new particles or forces appear to modify the running of couplings. That is a bold assumption. We already know the standard model is incomplete. It does not incorporate a quantum description of gravity. It does not explain dark matter. It struggled, in its original form, to account for neutrino masses. Cosmology tells us that the universe's energy budget includes components we can feel only through their gravitational effect. Within particle physics, there are puzzles about the pattern of masses and mixings that cry out for deeper structure. Any new physics at high energy additional fields, symmetries, heavy particles can change the shape of the Higgs potential. It can shift the boundary between stability and metastability. It can add terms that lift the deeper minimum or lower the barrier, or even create entirely new vacua with different properties. From this point of view, vacuum metastability in the pure standard model is less a final diagnosis and more a diagnostic tool. It tells us something about where new physics might begin to matter. If the Higgs mass had turned out very different, the story would change. The fact that it sits where it does, near the edge between stable and metastable, has inspired ideas that the universe might be tuned to a kind of critical point, balanced between phases in a way that is not simply accidental. Whether those ideas are correct is still open. The important thing is that the same data that suggest a metastable vacuum also tell theorists where to look for hints of deeper structure. That makes metastability less a doom scenario and more a signpost. There is a third reason for the absence of panic, and it has to do with how scientists learn to live with uncertainty. If you spend years working with models that are always approximations, with measurements that always carry error bars, you develop a kind of emotional callus around the unknown. You become comfortable holding multiple possibilities in mind at once. Perhaps the vacuum is truly stable. Perhaps it is metastable. Perhaps new physics will render the entire classification obsolete. You care about which is true. But you do not need a definite answer in order to keep working or to keep living. In that culture, headlines that scream, "Higgs could destroy the universe," land as a category mistake. They take a nuanced discussion about extrapolations and parameter spaces and reframe it as a horror story. Many physicists have had to stand up in public and say, over and over, this is a theoretical possibility, not a prediction, and certainly not something that should keep you awake at night. This gap between media framing and scientific practice is revealing in its own way. It shows how hungry we are, as a species, for clean narratives of danger and salvation, and how ill-suited those narratives are to the slow, probabilistic, conditional truths that physics often deals in. Behind all of this, there is a quieter shift in perspective that metastability encourages. In everyday life, we tend to think of risks as things that either demand action or can be ignored. If an asteroid has a non-trivial chance of hitting Earth in a few decades, we should do something. If the sun will swell into a red giant in several billion years, we can file that under trivia. Vacuum decay, with its fantastically long lifetime and its dependence on physics we do not yet know, falls firmly in the second category. But the very act of classifying it there forces a distinction between practical risk and ontological vulnerability. Practically, you are safe. Ontologically, you live in a universe whose laws may be rooted in a provisional vacuum state rather than an absolute minimum. Those are different statements. One speaks to survival, the other speaks to how you imagine the nature of reality. This is why some people find metastability oddly calming. It says, the universe does not come with guarantees, and yet here you are. Stability, in the sense that matters for your life, is already a miracle of scale. You do not need eternity for meaning. You need enough continuity to build, remember, and relate. On top of that, there is the possibility that the parameters we measure are telling us something deep. The Higgs mass, the top mass, the observed value of dark energy, the pattern of cosmic microwave background fluctuations. All of these fit into a picture in which the universe is balanced in a way that allows complexity to arise. Some see this as evidence for a multiverse, with anthropic selection picking out habitable vacua. Others hope for a dynamical explanation, in which the universe is driven towards states like ours by underlying principles we have not yet uncovered. In either case, the presence of metastability in our theoretical classification becomes less an isolated worry and more a thread in a larger tapestry. It is part of the story of how fine-tuned, or how self-organizing, or how contingent our cosmos might be. So no, there is no serious panic in the halls where these things are calculated. There is curiosity. There is the sober recognition that our best models have limits. There is the professional habit of treating dramatic possibilities as clues rather than prophecies. And for the rest of us, listening from the outside, there is an invitation tucked inside this calm. We can choose to see the metastable universe not as a ticking bomb, but as a reminder that the sense of security we build our lives on has always been a local, temporary arrangement. Our atmosphere, our climate, our biosphere, our societies, our bodies, all metastable structures. The vacuum, if it shares that character, is simply extending a pattern we already live inside. Once you accept that, another question emerges, less about physics and more about meaning. If even the background can, in principle, change, how do you find a way of living that does not depend on cosmic guarantees at all? At some point, when you stop expecting guarantees, you start wondering whether the universe we see is really the whole story, or just one lit window in a city that stretches beyond sight. Physicists have a dry phrase for a strange fact. The constants of nature look fine-tuned. Take the strengths of the fundamental forces, the masses of elementary particles, the value of the vacuum energy that drives cosmic acceleration. Change many of these by what, in everyday terms, would count as a small amount, and the universe becomes sterile. Stars might never form, or they might burn too quickly for planets to cool. Atoms might be unstable. Chemistry, as we know it, could never get started. You do not need exact percentages to feel the pattern. We seem to live in a narrow window of parameter space where complexity is possible. Outside that window, things still happen, but nothing that looks like galaxies, planets, brains. There are different ways to react to this. One is to say, perhaps we simply do not yet understand why the constants take the values they do. Maybe there is a deeper theory, as yet undiscovered, from which these numbers fall out uniquely. In that case, there is no fine-tuning problem, only a gap in our knowledge. Another response is to take the apparent delicacy at face value and ask, What if the reason the constants look tuned for life is that life can only arise where the constants fall into a small range? If there are many regions of reality, each with different vacuum states and therefore different effective laws, then observers will naturally find themselves in the rare pockets where the conditions allow observers. This is the anthropic line of thought. Steven Weinberg used this reasoning in a concrete way when thinking about the cosmological constant, the energy density of the vacuum. If the vacuum energy were much larger and positive, the universe would expand so rapidly that matter would never clump into galaxies. If it were large and negative, the universe would recollapse quickly. So, in a hypothetical ensemble of universes with different vacuum energies, observers would only arise in those where the vacuum energy is small enough and of the right sign to allow structure formation. Weinberg argued that, in such a setting, it would not be surprising to measure a vacuum energy, comparable to the density of matter at the epoch when galaxies form. Later observations found a small but non-zero dark energy density in roughly that ballpark. Anthropic reasoning is controversial. It does not explain why a multiverse exists, only why, if it does, we should not be shocked to find ourselves in a life-friendly pocket. For some, this feels like giving up. For others, it is a way to turn fine-tuning from a paradox into a selection effect. But talk of selection effects only makes sense if there is something to select from. One family of ideas that provides such a backdrop is eternal inflation. In the simplest inflation models, the early universe underwent a brief period of extremely rapid accelerated expansion, driven by the potential energy of some field. As that field slowly rolled down its potential, inflation ended, releasing energy that reheated the universe and led to the hot Big Bang. In many versions of the theory, however, the end of inflation is not uniform. Quantum fluctuations cause the inflaton field to decay in some regions, while in others it remains high enough to keep driving expansion. The regions where inflation ends form bubbles of hot, Big Bang-like universe. Between them, inflation continues, stretching space faster than the bubbles can fill it. The process goes on without end. New bubble universes keep forming inside an inflating background that never entirely stops. This is eternal inflation. Each bubble is causally disconnected from the others. Whatever happens inside one, its observers can never communicate with observers in another. Yet, in the larger picture, there is not a single universe but a multiverse. An enormous, perhaps infinite collection of bubble universes, each with its own cosmic history. If, in addition, the underlying theory has many possible vacuum states, then different bubbles can freeze into different vacua. In some, the Higgs field might settle into one value, in others, into another. Different vacua can have different effective constants of nature, different particle spectra, different patterns of symmetry breaking. Our universe, with its specific Higgs vacuum expectation value and dark energy density, would then be one region in a vast mosaic of possibilities. String theory, a leading candidate for a quantum theory of gravity, adds another layer to this picture. When you compactify extra dimensions in string theory, you can do so in a huge variety of ways. You can thread those compact dimensions with different configurations of flux. Each choice leads to a different vacuum, with different low-energy physics. Early work by Raphael Bousso and Joseph Polchinski suggested that, with enough flux choices, you could get a dense set of possible vacuum energies, a discretium, that might include values as small as the observed cosmological constant. Leonard Susskind popularized the term string landscape for this huge collection of vacua. In that landscape, the energy potential is not a simple sombrero with one rim and one deeper valley. It is a rugged mountain range, with an astronomical number of valleys, plateaus, ridges, and passes. Each valley corresponds to a different vacuum, with its own Higgs value, its own spectrum of particles, its own effective laws. Eternal inflation becomes a mechanism for populating this landscape with actual regions of space-time. The multiverse is the set of all those regions. Now, metastability looks different. In a single universe picture, a metastable vacuum might feel like a precarious accident, a weird and slightly alarming fact about our particular state. In a landscape populated by many vacua, metastable states are expected. Valleys, bounded by barriers, are everywhere. Transitions between vacua by tunneling become part of the dynamics. Our false vacuum, if that is what it is, could be a typical long-lived valley among countless others. This does not make it more or less dangerous. The lifetime calculation remains the same. What it changes is the context. Instead of asking, why would a unique universe choose a vacuum that is only metastable? You can ask, what kinds of vacua are most likely to be populated and to support observers in a landscape full of options? That is a different question. Of course, all of this is speculative. We do not have direct observational access to other bubble universes. If they exist, we cannot see beyond our cosmic horizon. We cannot measure the value of the cosmological constant in a neighboring valley. Critics point out that a theory that explains anything by saying somewhere something like this happens risks becoming unfalsifiable. Yet the multiverse and landscape ideas are not pure fantasy. They grow out of attempts to solve concrete problems. How to get inflation from simple fields. How to reconcile quantum field theory with gravity. How to account for the smallness of dark energy without absurd fine-tuning. They are driven by equations and consistency conditions, not by a taste for grandiosity. Our observational window, narrow as it is, still has something to say. The cosmic microwave background, mapped in exquisite detail by experiments like WMAP and Planck, shows a pattern of temperature fluctuations that reflects the distribution of quantum fluctuations stretched to cosmic scales by inflation. Those maps constrain the kinds of inflation models that are viable. They tell us, for example, that large, wild departures from simple, nearly scale-invariant perturbations are disfavored. They also place limits on signatures that might arise from bubble collisions in eternal inflation scenarios. So far, no clear evidence of such collisions has been found. This does not rule out the multiverse. It merely tells us that if other bubbles exist, either they are too far away or too few in number to have left an imprint in our observable patch, or their collisions produce subtler features than we can currently detect. The landscape, if real, is hidden behind an observational horizon. There are other, more radical ideas about the vacuum's nature. Some approaches treat space-time itself as emergent from more fundamental degrees of freedom, like an elastic medium emerging from atoms or a fluid from molecules. In these pictures, the vacuum energy might be a kind of residual, like surface tension, rather than a straightforward sum of zero-point energies. Eric Verlinder's emergent gravity proposals and causal set theory are examples of attempts to rethink space-time and vacuum energy at a deep level. If such ideas are right, the landscape might not be a literal catalogue of distinct vacua, but a higher-level description of collective behaviors. The multiverse, in that case, would be less a set of separate universes and more a space of emergent phases in a deeper underlying system. Whatever the details, the common thread is a move away from thinking of our universe as the entire, self-contained reality. Instead, our universe becomes a region, a phase, a solution, a vacuum among others. Temporary, not just in time, but in status. This can feel like a further erosion of meaning. If there are infinitely many universes, with all possible constants and histories realized somewhere, does that not flatten the significance of our particular one? If you can always say, elsewhere, something else happens, where does that leave the uniqueness you feel in your own life? Here, the physics can only take you so far. The equations do not tell you what to value. They do not pronounce on whether a life is more or less meaningful because there might be copies or variations of it elsewhere. They only suggest that what we see may be a tiny subset of what exists. One way to live with this is to notice that your experience has always been local. Even if there are no other universes, you will never meet most of the people on your own planet, never see most of the stars in your own galaxy, never know most of what happens even in your own city. The scale of the multiverse, if it exists, changes the numbers, but not the structure of your condition. You are always in one place, at one time, with one set of relationships and choices. Another way is to see the multiverse not as a threat to significance, but as a way to situate contingency. In a single universe, fine-tuning can feel arbitrary and oppressive. Why were the constants set just so? Why this vacuum? This Higgs value? This delicate balance? In a multiverse, you can say there are many vacua, many parameter sets. Most do not permit observers or permit only very simple structures. In the small subset that allow complexity, observers will find themselves. We happen to be in one such region. That does not make our region less real. It makes it one outcome in a broader pattern. Metastability, in this widened frame, becomes almost a psychological training ground. It teaches you to separate necessary from actual. It invites you to imagine that the rules you grew up with are not logically forced, but historically realized. It hints that if you were elsewhere in the landscape, you might not exist, or you might exist under very different conditions. There is one more twist. If the landscape is real and eternal inflation populates it, then vacuum transitions like the ones we fear as big slurp events are, at the larger scale, mechanisms for generating diversity. A bubble that destroys one vacuum region from the inside might create another region with its own physics. From the point of view of the multiverse, decay is also creation. The death of one effective universe is the birth of another. We will never watch this happen. Our causal patch is too small, our lives too short, our detectors too limited. But the math lets us sketch the outlines of such a picture, and in doing so, it asks us to reconsider what we mean by words like temporary and stable. Perhaps our universe is temporary, in the sense that a wave on the surface of the ocean is temporary. It rises, travels, dissipates, while the water that carries it continues. From the point of view of the wave, it is everything. From the point of view of the sea, it is one pattern among many, no less beautiful for that. If you let that image sink in, metastability and multiverse stop being competing anxieties and start to look like two perspectives on the same underlying reality. A reality in which the structures we inhabit are local steadinesses in a wider, restless field of possibilities. Stories have been circling these ideas for a long time. Long before words like vacuum metastability or landscape entered the conversation. They just gave them faces, and families, and endings. Take a world covered in dust. In the film Interstellar, Earth is not destroyed by a sudden catastrophe. It is dying by degrees. Crops fail. Storms roll across the plains, carrying soil into houses and lungs. It is a slow reminder that even something as taken for granted as a habitable planet is a kind of metastable arrangement. The climate, the biosphere, the thin strip of conditions that allow farms and schools and baseball games begins to slip. The story sends its characters into a universe that feels hostile and indifferent. They launch through a wormhole near Saturn, not because they crave adventure, but because the temporary stability of their homeworld is visibly ending. In that sense, Interstellar is an honest film about metastability. The safety you grew up in is only a chapter. Nothing guarantees another. Yet, the emotional center of the film is not the physics. It is a relationship between a parent and a child, stretched across light years and warped time. The black hole, the gravitational slingshots, the different planets with their different surface gravities, all serve as external expressions of a simple fact. The universe will not bend to keep your attachments easy. You are fragile beings negotiating a landscape that does not promise you anything. What is interesting, in the context of our question, is that the film does not offer a stable universe as its comfort. It does not say, "Do not worry, the laws are fixed, so everything will be fine." It says, instead, the universe is harsh and finite and indifferent. And within that, there are choices. People betray one another. Others sacrifice. Some cling. Some let go. The characters do not earn a permanent home. They earn the chance to keep going a little longer, to carry meaning into a new arrangement. That is what living in a metastable universe looks like when you turn it into a story. Not an answer, but a posture. Now move to a very different film, Everything Everywhere All at Once. On the surface, it is chaos. A tax audit. a crumbling marriage, a strained relationship between a mother and daughter, all wrapped inside a multiverse where every possible version of a life seems to exist somewhere. The main character is pulled between countless branching realities, each showing what she could have been if she had made different choices. Here, metastability takes the shape of sheer possibility. If the multiverse is real, and there are infinitely many vacua, infinitely many branches, then any particular life can feel small, almost meaningless. Why care about one laundry shop in one timeline when there are universes where you are a movie star, a rock, a chef, a corpse, or never born at all? The film's answer is quiet. It does not argue against the multiverse. It does not try to collapse the branches back into a single path. Instead, it lets the protagonist see everything, despair, under the weight of it, and then choose, deliberately, to care about the specific, messy, unglamorous life she actually has. The relationship with her daughter, the husband she had grown impatient with, the tiny acts of kindness available inside one small universe. It is the anthropic principle turned inward. Out of all the possible existences that might be realized somewhere, you find yourself here, in this one. You can either let that contingency hollow everything out, or you can treat it as the very condition that makes meaning possible, the fact that it could have been otherwise, and yet it is this. In a way, Everything Everywhere All at Once is a multiverse story that has nothing to do with physics and everything to do with psychological metastability. The protagonist's sense of self is unstable. Her various lives pull on her like different vacua. There is a temptation to fall into nihilism, to see the landscape of possibilities as proof that nothing matters. The resolution is not an appeal to cosmic purpose, but a choice to invest in one small patch of reality, to be present. That choice is exactly what living in a metastable vacuum demands from us. The vacuum may or may not be absolutely stable. There may or may not be other universes. None of that changes the fact that you occupy this configuration, with this body, these relationships, this interval of time. You do not escape contingency by inventing a larger backdrop. You learn to move through it. We have already mentioned Watchmen, a comic set in a world perpetually on the brink of nuclear war. Its emotional weather is a permanent late afternoon before a storm. People live, fall in love, make art, commit crimes, all under the shadow of possible annihilation. The world is metastable in a more immediate sense, a political arrangement that could collapse in minutes. Dr. Manhattan is the character who most resembles a physicist's fantasy. He experiences time non-linearly, sees past and future at once, knows the outcome of events, and still finds himself unable to answer the question, why? His detachment is not cruelty. It is the loneliness of someone who has internalized that the universe does not share human priorities. He knows that the seeming stability of the world is conditional. He watches people behave as if it were not, and he cannot quite decide whether that is delusion or courage. If you strip away the superhero costumes, Watchmen is a story about trying to be decent in a world where no one can promise you a future. It is metastability translated into political and psychological terms. The external threat is nuclear, the internal one is despair. These works are not footnotes to physics. They are parallel attempts to articulate what it feels like to exist inside an arrangement that might not last. You can see the same patterns in quieter stories, too. In films where relationships fall apart not because anyone is evil, but because people change. In novels where cities flood, where memories fade, where traditions erode, stability is always temporary. Meaning arises not from the assurance that something will endure, but from how people act while it does. The physics of false vacua and multiverses gives us one more layer of this same lesson. It says, even the laws are local. Even the constants are contingent. Even the background can, in principle, shift. That is the cosmic version of a breakup, or a political revolution, or a planet's climate tipping point. No guarantee that the pattern you know is the pattern forever. Stories help us practice for that. They put us in situations where characters cannot rely on permanence and ask, what then? In Interstellar, the answer is to cross terrifying distances, risking everything to keep some version of human culture alive a little longer. In Everything Everywhere All at Once, the answer is to stay, to choose softness in one tiny corner of the multiverse. In Watchmen, the answers diverge. Some characters double down on control, others walk away. One retreats to another planet entirely. None of these is the answer. But together, they sketch out a map of responses. Fight, flee, accept, create, care. When you think about vacuum metastability or the multiverse late at night, it is easy to get lost in abstraction, potentials, tunneling rates, landscapes of vacua. Stories pull those abstractions back into scale. They remind you that, whatever the universe is made of, you meet it as a person with a limited life, surrounded by other limited lives. The fact that the Higgs field might be perched in a long-lived valley does not tell you what to do when someone you love is afraid, or when your community is under strain, or when your own body starts to fail. But understanding that the universe itself is only holding temporarily can quietly shift your priorities. It can make the small, ordinary acts feel less trivial. It can undercut the fantasy that there will always be more time to say what you mean, to repair what is broken, to hold someone's hand. The films and stories that resonate most deeply with this theme are not the ones that offer escape from impermanence. They are the ones that let impermanence stand, unsoftened, and still find something worth doing inside it. Physics cannot tell you what that something is. It can only clear away a few illusions about how solid the floor is. The rest is up to you, and to the stories you choose to live by. At some point, after enough endings and almost endings, the universe stops feeling like a promise and starts feeling like a question it is quietly asking you back. If everything we have been talking about is true, or even partly true, then the picture looks something like this. The vacuum is not empty. It is a configuration of fields with energy and structure. The Higgs field, sitting at a non-zero value, is what allows particles to have the masses that make atoms, stars, and bodies possible. The numbers we have measured suggest that this configuration might not be the absolute lowest state, only a long-lived valley in a larger landscape. The expansion of the universe is accelerating, as if some small, persistent vacuum-like energy is pushing everything apart. And the equations that describe all this hint at other vacua, other possible universes, other ways the rules could have been. For us, none of that arrives as a laboratory experience. It arrives, if it arrives at all, late at night, when the world is quiet enough for the thought to land. The universe is only holding temporarily, not in the sense that it is about to end tomorrow, or that a true vacuum bubble is waiting just beyond the moon. In the deeper sense that the stability you depend on is not an absolute law, but the property of a particular state that could, in principle, have been different, and will not last forever on cosmic timescales. So what do you do with that? One possible response is to pretend you never heard it. Go back to treating the universe as a solid room with a locked door and no ceiling. Many people do, and there is no shame in it. Everyday life is demanding enough, without adding false vacua to the list. But if the thought stays with you, if it has already started to reshape the edges of how you see things, then a different response opens up. You can start by letting go of the idea that meaning depends on permanence. We often smuggle that assumption into our lives without noticing. We tell ourselves that a love matters if it lasts forever, that a book matters if it is remembered for centuries, that a civilization matters if it stands the test of time. Underneath those stories is a quiet belief: if something can be erased, it is less real. Metastability undercuts that. It says, on long enough scales, everything is erasable. Stars, galaxies, elements, vacuum states. There is no cosmic guarantee that anything you build will be preserved. The universe does not offer archival services. Once you accept that, the link between permanence and meaning begins to look fragile. A song that lasts 3 minutes can reach you more deeply than a tradition that lasts 300 years. A conversation that happens once can change a life more than a structure that has always been there. Duration and depth are not the same quantity. From this angle, the temporariness of the universe becomes less an insult and more a kind of framing. It tells you, the value of what you do cannot rest on its survival. It has to rest on how it is lived and shared while it exists. Another shift has to do with control. The idea of vacuum decay is frightening, partly because it represents a risk we cannot influence. There is no shelter, no mitigation strategy, no global policy that can lower the tunneling rate of the Higgs field. If it happens, it happens. If it does not, it does not. On human scales, the probability is so low that it disappears into the background. In contrast, many of the dangers we actually face are things we can affect. Climate change, nuclear weapons, pandemics, the slow erosion of democratic structures. If you spend your fear budget on vacuum decay, you are borrowing anxiety from a domain where you have no agency and spending it where you could have a metastable philosophy, if you want to call it that, would try to line up fear with influence. It would say, accept fully that some kinds of instability are outside your reach. Then, turn your attention toward the instabilities you can shape. The vacuum's lifetime may be fixed. The lifetime of a culture's better instincts is not. The cosmological constant may be beyond your vote. The conditions in your own community are not. Seen that way, learning that the universe might be only temporarily stable is oddly liberating. It clarifies where your circle of control ends. It invites you to invest your energy where it can actually change something, instead of chasing an illusion of safety at the deepest level. There is also the matter of timing. You happen to be alive at a very specific era in cosmic history. Long after the first stars ignited, long before dark energy has stretched distant galaxies beyond our horizon, after the universe has cooled enough for complex chemistry and biology, before it has diluted matter so much that new star formation dies away. You exist in a narrow window where there are both observers and questions. From all we can tell, you also live at the only time when beings like you can measure these things. A few billion years earlier, the cosmic microwave background was harder to observe, and the acceleration of the universe was not yet dominant. A few trillion years from now, if any observers exist, they might see only a single, merged galaxy and a dark sky, with no clear evidence of cosmic expansion, no microwave background, no accessible trace of the larger structure. In that sense, your existence is a double coincidence. You are not only in a universe whose vacuum and constants allow complexity, you are in the brief phase when the universe is transparent about its own past. If you are looking for a kind of fragile, contingent meaning, that is not a bad place to start. You can think of your life as a small excitation in a sea of fields, arising at the one time those fields are arranged in a way that lets you ask what they are. The universe, through you and others like you, gets to look back at itself and say, this is strange. That is not a purpose assigned from outside. It is an emergent property, fields configured in such a way that they can reflect. What you do with that reflection is up to you. You could use it to retreat, to declare everything meaningless because it will not last. Or you could use it as motivation to pay attention more fully. If you know that mornings, embraces, and music are temporary, at every scale from the biological to the astrophysical, you can either numb yourself or you can let that knowledge sharpen your presence. None of this requires heroics. Most of the time, living inside a metastable universe looks ordinary. You make breakfast. You answer messages. You stand in line. You notice a patch of sunlight on a floor. The vacuum holds. The Higgs field continues to give mass. The dark energy continues its slow push. Somewhere, telescopes stare at the sky. Colliders smash particles. Data trickles onto hard drives. Between those ordinary moments, there are decisions. To tell the truth or not. To apologize or double down. To make art or skip it. To reach out or stay silent. These are the places where meaning accumulates, grain by grain, inside a universe that will not keep the record forever. The Trinity test, back at the beginning of this story, was a moment when humans pressed a button under theoretical uncertainty. They did it for reasons that were tangled and imperfect. Fear, war, curiosity, ambition. The atmosphere held. The vacuum did not ignite. The world went on, altered. Today, the uncertainties you live with are different. You are not deciding the fate of the sky. You are deciding how to move through a world where the sky, in the deepest sense, has no guarantee to offer you. That can sound like a loss. In another key, it is an opening. If the universe is only holding temporarily, then everything you cherish is already a bonus. Every conversation, every laugh, every night drive past city lights, every moment of understanding another person a little better exists against a backdrop that did not have to be here and will not always be. You do not need eternity for that to matter. You just need to notice that it does. And somewhere, unimaginably far in the future, perhaps a new vacuum bubble will form and erase everything that remembers you. But between now and then, even if then is as far from you as you are from the first atoms, the fields will keep trembling in their current pattern long enough for you to live an entire life inside this temporary holding. What you do with that life is not written in any potential. It is not dictated by metastability or dark energy or the mass of the Higgs. It is the one part of the story where the equations step back and leave a blank space. You, small and temporary, get to write in it.